Welcome to this lesson on Boolean blindness. Today we're going to tackle one of the most common yet overlooked sources of bugs in software development. By the end of this lesson, you'll be able to recognize Boolean blindness, patterns that lurk in your code, and you'll learn 5 specific refactoring techniques that eliminate Boolean confusion. We'll show you how to write self-documenting code that prevents frustrating bugs. And most importantly, you'll discover how to design APIs that make illegal states impossible to represent. So, what is Boolean blindness? Boolean blindness occurs when we use bare true and false values to represent rich, meaningful information. Now, here's the core problem. To the compiler, all Booleans look identical. And this sameness becomes a perfect hiding place for bugs. Let me show you what I mean with a quick example. Look at this function call. Which boolean is which? Without looking at the function signature, you have no idea. Now, compare it to this version. The difference is immediately clear. The second version tells you exactly what each parameter means. Here's a key insight that will guide everything we discuss today. When code requires comments to be understood, the types aren't doing their job. Types should be your first line of documentation, and they should be impossible to ignore. Now that we understand the basic concept, let's explore the 5 most common way Boolean blindness manifests in real code. The first and most dangerous pattern is the parameter swap pattern. This creates bugs that perfectly compile but behave completely wrong. Now, here's a typical example. Now, when somebody calls this function by passing true for the first parameter and false for the second one, they intend an email to be sent, but not to make Alice the admin. But what if they accidentally swap the parameters? Alice becomes an admin and no welcome email gets sent. The compiler won't catch this. Your tests might miss it. It just silently does the wrong thing. Now, the fix in most of these parameter swap cases is to use wrapper types. Instead of raw booleans, we create specific types for each concept. Now, when you call this function, you must be explicit. If you try to swap the parameters, the compiler stops you immediately. This approach turns runtime bugs into compile time errors, which is exactly where we want to catch them. The second pattern occurs when a false value tells you something failed, but not why it failed. This leaves you guessing about what went wrong. Now, consider this function. When success is false, what actually happened? Was the flight full? Was the booking ID invalid? Did the payment fail? You simply don't know. The solution uses discriminated unions to capture all possibilities. Now, your function can return specific information about what happened. Instead of meaningless something went wrong, you get exactly what went wrong. This lets you handle each case appropriately and provides better user experiences. The third pattern happens when different parts of your system start reusing the same boolean for unrelated purposes. This creates unexpected dependencies between features. Now, here's how it typically unfolds. Starting off with a simple admin flag. But someone on the UI team decides that admins should get dark mode by default. Later, the business decides to remove admin rights from contractors. Suddenly, contractors lose dark mode and nobody understands why. The fix is to separate these concerns completely. Now, the UI code can't accidentally couple admin rights with user preferences. The rule here is simple: one Boolean, one responsibility. When you need to represent multiple concepts, use multiple types. The fourth pattern occurs when the same validation logic gets repeated throughout your application layers. This happens because you can't trust that a string parameter is actually valid. Look at this common anti pattern. Every layer here revalidates the same data because nobody trusts the previous layer. This is wasteful as well as error prone. The solution lies in validating once at the boundary and using the type to maintain that guarantee. Now, the validation happens exactly once at the user controller layer. You are passing at the boundary and you trust the type everywhere else. This eliminates redundant validations and makes your guarantees explicit. The final pattern happens when you use multiple booleans to represent what should be a single state machine. This makes illegal states representable and creates confusion about valid combinations. Now consider this order class. Can something be shipped and cancelled at the same time? What about delivered and returned? The booleans don't tell you which combinations make sense. The fix is to model the actual state machine. When you have the state machine, your order class can go ahead and enforce business rules. This approach will model the business rules directly in code rather than fighting them with complex Boolean logic. Now that we've seen the 5 patterns, let's create a practical checklist. Before you write Booleans anywhere in your code, ask yourself these 5 questions. First, can parameters be swapped? If yes, use wrapper types. Second, does false hide the real reason for failure? If yes, use discriminated unions. Third, are these concerns actually separate? If yes, use dedicated types for each concept. Fourth, will this Boolean travel through many layers of your application? If yes, validate at the boundary and use type to maintain the guarantees. Fifth, are there really only 2 states or is this part of a larger state machine? If it's more complex, consider enums or explicit state machines. This checklist will help you catch Boolean blindness before it becomes a problem. Now, when you start to refactor existing code, follow this practical migration strategy. Start at module boundaries by wrapping public APIs first. This gives you the biggest impact with the least disruption. Use your IDE's refactoring tools to handle repetitive changes. Most modern IDEs can rename types and update all usages automatically. Create adapter functions to bridge old Boolean APIs with new typed ones. This lets you migrate gradually without breaking existing code. Enable strict compiler checks to catch exhaustiveness violations early. Languages like TypeScript and modern Java can warn you when you haven't handled all possible cases. Now, let's wrap up with the big ideas of this lesson. Booleans are not self documenting, they need context to be meaningful, and that context often gets lost. Type systems are the documentation that can't lie. Use them to encode your business rules directly in code. Illegal states should not be represented. Design away entire classes of bugs by making wrong code impossible to write. Parse at boundaries and trust types everywhere. The key mindset shift here is stop thinking what data do I need? Start thinking what states are legal in my domain. When you design types around legal states, Boolean blindness disappears naturally. You now have 5 powerful techniques for eliminating Boolean blindness from your code. These patterns will help you write more reliable, self documenting software that prevents entire categories of bugs. Remember, every Boolean is a design decision. Make sure you're making a good one. Thanks for watching, and I'll see you in the next lecture.